All right, we're going to try to find points of inflections for this equation on this interval. So we got to do to get a point of inflection, you have to find the second derivative. So when you derive sine x, you get cosine x. When you derive cosine, you get negative sine. Then if you derive this again for a second derivative, this gives you negative sine. This gives you cosine. Keep the negative. Then if I set this equal to 0, move the cosine over, I look at this and go, okay, when will sine and cosine be opposites of each other? And what you do is you look at your unit circle and realize, hey, at these two values, they're both going to be square root of 2 over 2, but one's positive, one's negative. So those are my two values where they're going to be opposites of each other. So we take these two values, they're our breakpoints, and we're going to check to see if it actually changes concavity. And when you plug in a value from this interval, you get a negative. A value from this interval, you get a positive. A value from this interval, you get a negative. And again, you're plugging it into the second derivative. And what you notice is it does change concavity, so that is a point of inflection. It does change concavity, so it is a point of inflection. Now, if it didn't change concavity, it would not be a point of inflection. So what they did, so it is. So we find the output at these two breakpoints by plugging it into the original function, and those are my points of inflection coordinates. The coordinates of my points of inflections. Again, it has to change concavity at a point of inflection. When you do the second derivative equal to 0, you're finding where it possibly could be. Now the second derivative test is different. We're trying to find relative extremas using the second derivative. So for this equation, I first find my first derivative. So up to 1/2, leave the inside, drop the power by 1. Remember, square root's 1/2 power. Derive the inside as 2x. When I break this down, I leave the 2x on top. This 2 and this square root x squared plus 1 goes to the bottom. 2's cancel. So I have this. Now, from here, I set the top equal to 0 and the bottom equal to 0. And this gives you 0. This ends up having no solutions because when you solve this, it's imaginary, plus or minus I. We don't deal with imaginaries right now. And oh, by the way, why did we take the first derivative and set top and bottom equal to 0? We're trying to find critical numbers. Critical numbers are where second derivative tests, meaning finding extrema, are going to be. They're going to be at critical numbers. So the only critical number we have to deal with is 0. And for second derivative tests, what we're going to do is plug our critical number into the second derivative. So I take this, I'm going to derive it using quotient rule. So you derive x, leaving you 1, leave the bottom, put it right there, minus, leave the top, derive the bottom. What's cool is I derived this bottom already, same thing. So it's just simply, this equation itself is the derivative. So I just take this value, put it right there, and then square the bottom. So you square this value. So when you do that, right here, since it's fraction right here, I needed to multiply top and bottom right here by this value on the denominator. So I multiply top and bottom by that. That would drop the square root off. This x times x gives you x squared. Since they both would now have the same denominator, you put it right there. When you square a square root, it's off. So it's just simply this when you square a square root. Now this simplification of the top can be a little cumbersome, but hopefully you're getting better at those. Now this and this combine, leaving you 3/2 power. X squareds cancel, leaving you just 1. There is your second derivative. And you simply plug in 0. The one value that could be a max or min, your critical number. And when you plug it in, you get 1. 1 means it's concave up, because it's positive, which means that at 0, it's up. So that means that is going to be a relative min. And we found the actual coordinate by plugging 0 into the original function, and it came out to be 1. So 0, 1 is a relative min using the second derivative because it was concave up at that point. So find your critical numbers, plug your critical numbers in the second derivative. Now you didn't actually have to simplify this down to here. You could have plugged 0 in up here and deal with all the math. It would be just as easy. And if you like that and instead of dealing with simplification, do it.